Welcome. In this video, we're going to explore linear regression using some data from a grocery store. So what I have for us here is grocery store data that's been taken from a CSV file and stored as an Excel file. Let's explore it. So we have the customer ID, and we can see that the data is currently sorted by customer ID. That's pretty straightforward, and zip code as well, where those people live by zip code. We have number of purchase visits. So this is not just plain visits, it's actually the customer purchased something during this visit. So let's explore that a little bit with some summary statistics here, descriptive statistics. So we're doing the summary statistics. And we can see that the mean is 5, median's 3, mode is 1. So most often people are just visiting one time. We can see the range here is 114, so 1 to 115. One of the things that we're missing from this data is any sense of time. So they visited, this particular customer in row 2 visited twice, but was that twice in a week? Well, because there's a customer that visited 115 times, I'm inclined to think that's not a week. In fact, 115 would be once a day for nearly 4 months. So obviously, if we were working with the grocery store, we could go back and ask them or be more specific in requesting certain data for a time period. You don't always have that opportunity, and sometimes you have to make assumptions about data, and so we're going to make an assumption that this is data collected on an annual basis. So the 115 fits with that. 2 visits, someone could have visited the grocery store only twice during that time, so they obviously are not a regular customer. Okay, so and then we have, what do we have? Uses credit card. A 0 means they don't, a 1 means they do. But again, we're going to have to make some assumptions here. In the first row, they had 2 visits, so did they use cash on both visits? That would make sense. But what about this one? Uses credit card. They have 4 visits. Did they use a credit card on all 4 visits, or did they just use a credit card once? We don't know. We would need to get that information clarified so that we could better use this data. Now we're using a dummy variable here for users credit card, the 0 and 1 that you can see there. And we're going to have to make an assumption that if it means, or if it has a 0, that it means they always use cash for every visit. And if it has a 1, it means that they always use credit card for every visit. And while that's somewhat normal, people tend to be in a habit of using one or the other. There are some who mix it up and occasionally use a different method. Perhaps maybe more so the credit card users who occasionally use cash. But nonetheless, we have to make an assumption, so we'll make one there. And then the next one we have is gross margin percentage. So 0.6, 0.54, we're making a certain margin on what we sell. So we sell $1, we're making a margin of 0.54. This is obviously good to know. We're talking about a business. We don't want to just know what we're selling. So we have a total sales over here of $368 for 2 visits, and then an average sale per visit of $184.23. And we know that it was 0.6. Now, because the data is sorted by customer, we don't know if this 0.6 is good, if it's normal. We can scan down this, but let's just run some descriptive statistics on this and see what we learn. So what do we learn about the descriptive statistics? We learned that the mean is 0.51, so that 0.6 that we saw wasn't far off, that the mode is 0.59, okay? The range is quite wide, 7.45. We have a maximum of 0.99. That means we've made nearly 100% off of a particular customer. So they're buying the items we want everyone to buy. But we've lost 646% on at least one customer, maybe more. That seems odd. It could be bad data. Let's explore it a little bit more by sorting. Let's sort by this gross margin percentage. So you can see that we have the attributes have full names, which are long, but they're very helpful when you're doing something like this. So gross margin percentage, we're going to go smallest to largest because we want to see that negative. So negative 6.46. The person visited one time, bought an item for $1.99. Yeah, I think this could be valid data. Again, we would have to maybe dig into it more and have specific information about the products that were purchased by these customers. That would be helpful. But often a sale is advertised, and the sale item is a lost leader, meaning that we're going to lose money on it, but most of the people who come in will buy more items than just that. Nonetheless, we are losing money on a number of customers. In fact, some that visit multiple times during the year, we have a negative gross margin on. Obviously, that's not ideal, but it looks like it's valid data, so we'll move forward. The next column is microvision market segment, and you can see that there are numbers here, 38, 8, 11. So what does that mean? Well, there's a company that has developed these market segment, and it's an actual system, and we've got a PDF of that where they explain how they developed it and what's behind it. And then if we scroll down to section 2 of this paper, we get a description of what each of these numbers mean. So number 1 is upper crust, number 2 is lap of luxury, established wealth, and we can read about what it means. And if we scroll down, we can see that there are 50. I won't go all the way, but there are 50 of these categories. So that's what it means in here with this microvision market segment. And somehow the company has been able to identify these purchasing customers. Maybe they have a loyalty system where the customers have signed up to be a part of that loyalty system. And in doing that, they answered some questions, which allowed the grocery store to mark these based on their microvision market segment. We were talking about the total sales, so let's sort by that. And let's sort largest to smallest. So our big fish are just at $24,000 for the year for all of the purchases that they've made, out with 31 visits, 41 visits, and 22,000. Let's do our descriptive statistics on those total sales. Okay, so the mean is 4.73. The median is 261.98 for the mode. Okay, we have a range of 99 cents to 24,000. Okay, looks like it could be valid. So we've talked in a previous video about how to separate data, segment the data using the advanced filter. But let's use the box plot to take a look at total sales by credit card usage. So what we're going to do is insert a box plot with our total sales. And then notice that there's really no X value here, so we need to go up and change that. So here we have our box plot. We're looking at total sales and credit card. So it's not, the box plot itself is, wow, really squished down because most of the sales are down in this lower range. That bar that's right here indicates all of the ones above it are outliers. And we have the bar right here, and these are all outliers. And then our box represents the first quartile and the third quartile, but it's really squished down. We can adjust that. Let's go into our settings and adjust our vertical axis to, let's adjust it to maybe 3,000, I'm guessing here. Yeah, that gives us a better picture of our box plot. So we can see where the upper bound is, and then those outliers go up, and we know they go quite a ways up, especially for the credit card, the ones. We can see the X now, which is our mean, and the line here, which is our median that divides it. And of course, our bottom of the box is our first quartile, and the top of the box is the third quartile. So for those who use a credit card, we're looking at the first quartile being pretty close to the third quartile for those who just pay with cash. So in general, people are spending more money if they're using a credit card versus just paying with cash. So a box plot is a great way to explore data. All right, well, beyond exploring data, let's get into our linear regression. And I'm going to walk through this process, and then we'll talk about all the steps involved. So what I'm going to do is data analysis tool pack, and I'm going to select the regression option here. And for my Y input, this would be my response variable, sometimes called the output variable, sometimes called the dependent variable, the thing that I'm trying to determine. And so this is going to be my total sales. And then my input is the predictor variable. So the thing, can I predict Y from X? Can I predict that response variable from my predictor variable? And so in this case, my predictor variable, for the sake of doing this first one, we're going to do the zip code, and we have labels. I'm going to go ahead and leave it to the new worksheet, simply because it's a little easier to explore that way. Okay, the first thing to note on this is that nowhere in this output does it list our response variable, which is total sales. So we can just replace this tag up here, summary output, with total sales, and make that bold. And that just tells us what a response variable was or is for this summary. Down here, we can see our predictor variable. We just have one. And eventually we'll work with the equation that comes from these numbers down here. But for this example, just to note that this is where our predictor variable is, and also to note that we're interested in this R squared. So this is a percentage, and we can convert it to a percentage. That's the easiest way to look at this. It's a rather small percentage, so we're going to have to increase the number of decimal places here. So what this is saying with this R squared is that for our predictor variables, in this case one variable, zip code explains 0.06% of the variation in total sales. So the R squared is called our coefficient of determination. And it simply tells us how much this predictor variable explains about the variation in our response variable. Now, 0.06% is not much, and frankly, not enough to even work with from this standpoint. But if we put our business hat on and we think about, well, what if zip code was at if it had an R-square of, say, 10%, an R-square of 15%, something like that, well, then we might want to modify our marketing approach so that we took zip code into account. But it's low, so it's 0.06%, that coefficient of determination. So it doesn't really influence the total sales. But from the standpoint of our business hats, putting our business hats on, we have kind of a larger question we have to ask. The larger question that we need to ask is, what are we actually trying to accomplish here? Do we want to increase sales, or do we want to increase profits? And let me illustrate what I mean. So we can see in the total sales column that we have 24,000, 22,000, 15,000, 14,000. Those are all great numbers. But notice that we're not making the same amount from all of these. And we know that because the gross margin percentage. So we're making 0.59 on 24,000 and we're making 0.62 on 22,000. So do we want to just increase our gross sales, or do we want to increase our gross margin percentage? And from a business perspective, we want to increase that gross margin percentage and combine with the total sales. So of total sales, we want to increase gross margin percentage. So we can calculate a total gross margin for our customers and simply do E2 times G2, and we come up with that amount for that particular customer. And let's copy this down. Now I'm going to double click right here. So notice how my mouse icon has changed from the normal icon to when I hover over that green box in the lower right hand corner of the cell, it's a much tighter cross, a black cross there. And if I just double click on that, it populates the entire column of data clear down to the end, and we can verify that simply by doing a control down, and that'll take us to the last row, and notice that that populated down to that last row. So when you're working with large data sets, that's much faster. In fact, maybe it's faster all the time. So now let's take a look at, say, rows 3 and 4 here. So gross sales of 22. Actually, let's take a look at 4 and 5. A gross sale of 15,800 versus 14,200, but our total gross margin of 9,150 versus 9,375. So we've actually inverted the order of these as far as the value of that customer to us. And in fact, what we want to do now is to sort our data based on that calculated column. And we want to go largest to smallest. And we can see from this that, we have a couple that are inverted there. We have other ones down here, an 8,000 above a 9,000. So it pays for us to pay close attention to that gross margin percentage, and also pay close attention to what we're actually trying to accomplish from a business perspective. Now we'll use total gross margin as our response variable, and let's check that against, say, credit card as the predictor variable and see what we come up with. What we can see from this is that our predictor variable, which uses credit cards, is responsible for explaining 9.5% of the variance in total gross margin. So that's an important amount. So let's play around with the equation. So we're going to work with these numbers down here. And the equation follows the basic format for the equation for a straight line, which you may recall is this equation here, y equals b plus mx, where b is representing that y-intercept, and m is our slope, and x is the x value. And all of that can predict the y value if you have all of those things. So we're going to build an equation using these numbers down here. The intercept is our b. The coefficient for uses credit is our m. And then the x becomes whatever the amount for uses credit. In this case, it's either a 0 or a 1. So for any given customer, we would plug that in and could get the actual number. So let's write that equation out. So total gross margin, which is our y, equals 159.94 plus 234.32 times uses a credit card. Okay? So we could implement that formula to find out how well it predicted, knowing that it's only explaining about 9%, 9.5% of the total gross margin. Now this is what is called a simple linear regression. And because this formula uses one of the predictor variables. And Excel has a nice feature that you can add a trend line. So if we take our total gross margin and we insert a scatter plot, and we've done this before, but I'll tie it into what we're talking about today. For my X value, I'm going to choose the number of visits rather than the user's credit card, because the user credit card is a dummy variable, a 0 or 1, and the graph's not really that interesting when we plug that in. But the number of visits provides more variety and gives us more insight to looking at the linear trend line, with the R squared and even the equation added to it. So once I set that up, I have my scatter plot with my total gross margin on the y-axis, and then the x-axis is the number of visits. And then I can add a trend line. Now notice that when I add a trend line, it defaults to a linear trend line. Excel has other options, but we're working with a linear regression, so we want that linear trend line. And also notice that it's not the color and size that we want by default. Now what we can do here is we can scroll down to the bottom and we can have it display both the R square on the chart and the equation for us, just like if we had done the linear regression through the data analysis tool pack. Now obviously it doesn't give us all the other data points, all the other calculations, but it does give us these two items, and we can even increase the size of that so it's more readable. So there you go. We have our equation. We can see that the y-intercept, 71.871, right? That would be the intercept on the linear regression from the data analysis tool pack. We can see that the coefficient for our number of visits is 35.29, and we can see that the R square is 37.4%. So let's just call it 37%, so that we know that the number of visits explains 37.4% of the variation in the total gross margin. So this is another way of getting similar information. The examples so far have been for a simple linear regression using one of those predictor variables. So let's let's try a multiple linear regression with multiple predictor variables. Now our response variable is going to be the same with total gross margin, but let's use both number of visits and uses credit cards as our predictor variables. Okay, what we can see from this is that the combination of two predictor variables, number of purchases per visit, number of purchase visits and uses credit card account for 38.3094% of the variation in total gross margin. Now, we can build the equation from this, but before we do, I want to point out a couple of other aspects of this. Notice that there is a degrees of freedom here, DF, for the regression. Now, that is simply the number of these predictor variables that I have. So we have two. If we go back to one of the others where we just had a simple linear regression equation, it would have a 1 there. Also, notice that we have a significance here of 0, the significance of f. This is the p-value for f. And I'm pointing that out because we want that to be below the 0.05, whatever our alpha is. So in this case, we're doing a 95% confidence level, which has been explained in a previous demonstration. So we want this to be below that 0.05, and it is. If it was above 0.05, we would say that these predictor variables do not predict this total gross margin, so that we might have an equation, but the equation itself is not good. So, and then much like that for the entire equation, we have the p-value for number of purchase visits and uses credit card, and both of those we want below the 0.05 alpha, and they are. All right, so this is a good equation, and we can plug these numbers, well, all three of these numbers, into our equation, and we know that it represents 38.3094 of the fluctuation in total gross margin. So here's what that equation looks like. So total gross margin equals that 52.86, our intercept, or y-intercept from the formula, plus 33.13 times the number of purchase visits, that comes from right here, plus 78.01 times the uses credit card. Now, I should point out that because we're working with dollars, these are actual dollars, and so we might say something like this. Here are the two statements that we can say about what this equation tells us. That each additional visit will increase the total gross margin by 33.13, $33.13, everything else being equal. And that to get customers to use credit cards will result in a per period increase of $78.01. And we are assuming that per period is 1 year. Now, all of that is considering that it's only defining or explaining 38.3094% of total gross margin. Excel does not have an easy way to do a scatter plot with a trend line for the multiple regression analysis, so where we're using more than one predictor variable. But we can use this formula to create a new column, a calculated column, and we'll do that, and then we can produce our scatter chart and produce our trend line and show the R value. We can't show the equation because we're implementing the equation to create the data column, the attribute. So we'll simply label this. Let's create a little space in there, and we're going to label this visits plus credit card, and we need to implement that formula. So I'm looking at the formula off screen, and I'm going to type in first of all our intercept, so plus, and this will be our number of visits, so C2 times, and then that's the constant for C2, or if you will, the M for C2, although it's not a slope. And then we want that to be added to the uses credit times the constant for that, or coefficient. I called it a constant, it's the coefficient. Now I do prefer to use parentheses around these just to be thorough, so I'll type those in. And there you go, we have our calculation. So keep in mind that this equation accounts for approximately 38% of the fluctuation in total gross margin. And so that's really what we're calculating here, and that's why there's this big spread between what we're seeing in the actual total gross margin and what we're seeing with our linear equation. Now we can copy this down, and then we can chart this along with the total gross margin as we did previously with the total gross margin and number of visits to get a scatter plot, put our trend line, and then plug our R square value in there. Okay, you can see from this that we have our total gross margin here, and we have the combination visits plus credit card here, and we have our trend line with our R square value, and that R square value matches what we found with doing the multiple linear regression with the data analysis tool pack. And we can take a look at that, 0.3831, and there you go, right here. Now it's giving us the R square, and what we want to use is the adjusted R square, and I didn't really explain that, why we're using adjusted R square. The adjusted R square takes into account both the number of observations, but also, and more importantly, the number of predictor variables that we're using. So if you have one predictor variable, you're going to use the R square, which is what's displayed on the scatter plot. But if you're using multiple predictor variables, you need to use the adjusted R square. If you're working on a project where you're trying to figure out which combination of attributes have the highest percentage for explaining the variation in your response variable, then you're going to want to look at that adjusted R squared value. So you can plot this and you can display the R square, but not the adjusted R square value. Wow, that's a lot to take in. So the best way to learn this is for you to dive in and practice to do some simple linear regression with a single predictor variable and multiple linear regression with multiple predictor variables. For this data set, I have not shown you which combination of attributes as predictor variables have the highest percentage for explaining the variation in that response variable, total gross margin. So there you go, some opportunity to explore and see if you can find which combination of predictor variables do the best job.